This video is part of a larger series on using large language models in practice. In the previous video of this series, we saw how we can efficiently fine-tune a large language model to respond to YouTube comments in my likeness. While the fine-tuned model did a really good job at capturing my style when responding to most YouTube comments, it didn't do so well when responding to technical questions, which required more niche and specialized knowledge. In this video, I'll discuss how we can improve LLM-based systems using Retrieval Augmented Generation, or RAG for short. I'll start with a high-level overview of RAG before diving into a concrete example with code. And if you're new here, welcome. I'm Shah. I make videos about data science and entrepreneurship. And if you enjoy this video, please consider subscribing. That's a great no-cost way you can support me and all the content that I make. A fundamental feature of large language models is the ability to compress world knowledge. The way this works is you take a huge slice of the world's knowledge through more books and documents than anyone could ever read in their lifetime, and you use it to train a large language model. And what happens in this training process is that all the knowledge and concepts and theories and events that have happened in the world that are represented in the text of the training data, they get represented and stored in the model's weights. So essentially what has happened is we've compressed all that information into a single language model. While this has led to some of the biggest AI innovations the world has ever seen, there are two key limitations for compressing knowledge in this way. So the first limitation is that the knowledge that is compressed in a large language model is static, which means that it doesn't get updated as new events happen and new information becomes available. And for anyone that's used ChatGPT and tried to ask it a question about current events, probably have seen a message like this. As my last update in January 2022, I don't have access to real-time information, so I can't provide specific events from February 2024. The second limitation is that these large language models are trained on a massive corpus of text. The result of that is that they're really good at general knowledge, but they tend to fall short when it comes to more niche and specialized information, mainly because the specialized information wasn't very prominent in their training data. And so when I asked ChatGPT how old I was, it said that there was no widely available information about Shahin Talebi's age. He might be a private individual or not widely known in public domains. One way we can mitigate both of these limitations is using Retrieval Augmented Generation, or RAG for short. Starting with the basic question, what is RAG? This is where we augment an existing large language model using a specialized and mutable knowledge base. So basically, we can have a knowledge base that contains domain-specific information that is updatable, where we can add and remove information as needed. The typical way we'll use a large language model is we'll pass it a prompt and it will spit out a response. This basic usage will rely on the internal knowledge of the model in generating the response based on the prompt. If we want to add RAG into the mix, it would look something like this. So instead of starting with a prompt, we'll start with, say, a user query, which gets passed into a RAG module. And what the RAG module does is that it connects to a specialized knowledge base, and it will grab pieces of information which are relevant to the user's query and create a prompt that we can pass into the large language model. And so notice that we're not fundamentally changing how we're using the large language model. It's still prompt in and response out. The only thing we're doing is augmenting this whole workflow using this RAG module, which instead of passing in a user query or prompt directly to the model, we just have this pre-processing step to ensure that the proper context and information is included in the prompt. One question you might have is, why do we have to build out this RAG module? Can't we just fine-tune the large language model using specialized knowledge? so that we can just use it in the standard way? And the answer to that question is yes. So you can definitely fine-tune a large language model with specialized knowledge to teach it that information, so to speak. However, empirically, fine-tuning a model seems to be a less effective way of giving it specialized knowledge. And if you want to read more about that, you can check out source number 1 linked in the description below. With this basic understanding of what RAG is, let's take a deeper look into this RAG module to see how it actually works. The RAG module consists of two key elements. First is the retriever, and second is the knowledge base. So the way these two things work together is that a user query will come in, it'll get passed to the retriever, which takes the query and searches the knowledge base for relevant pieces of information. It then extracts that relevant information and uses it to output a prompt. The way this retrieval step typically works is using so-called text embeddings. Before I talk about how we can use text embeddings to do search, let's talk about what they are exactly. Put simply, text embeddings are numbers that represent the meaning of some given text. So let's say we have a collection of words like tree, lotus flower, daisy, the sun, Saturn, Jupiter, basketball, baseball, satellite, spaceship. Text embeddings are a set of numbers associated with each word and concept that we're seeing here. But they're not just any set of numbers. They actually capture the meaning of the underlying text such that if we are to plot them on an XY axis, similar concepts are going to be close together, while concepts that are very different from each other are going to be spaced far away. Here we see plants tend to be located close together, celestial bodies tend to be close together, these sports balls tend to be close together, and things that you typically see in space tend to be close together. And notice that the balls are closer to celestial bodies than they are to, say, plants, because perhaps balls look more like celestial bodies than they do plants and trees. So the way we can use this for search is, say each of these items is a piece of information in our knowledge base. You know, we have some description of this tree, a description of this lotus flower, the description of Jupiter, and so on and so forth. What we can do is represent each item in our knowledge base as a point in this embedding space, and then we can represent the user's query as another point in this embedding space. And then to do search, we simply just look at the items in the knowledge base that are closest to the query and return them as search results. That's all I'll say about text embeddings and text embedding based search for now. This is actually a pretty rich and deep topic, which I don't want to get into in this video, but I'll talk about in the next video of this series. Next, let's talk about the knowledge base. Say you have a stack of documents that you want to provide to the large language model so you can do some kind of question answering or search over those documents. The process of taking those raw files and turning them into a knowledge base can be broken down into 4 steps. The first step is we'll load the documents. What this consists of is getting together the collection of documents you want to include in the knowledge base and getting them into a ready to parse format. The key thing here is that you want to ensure the critical information in your documents is in a text format, because at the end of the day, large language models only understand text. So any information you want to pass to it needs to be in that format. The next thing you want to do is chunk the documents. The reason that this is an important step is that large language models have a fixed context window, which means you can't just dump all your documents into the prompt and pass it to the large language model. It needs to be split into smaller pieces. And even if you have a model with a gigantic context window, chunking the documents also leads to better system performance because it often doesn't need the whole document. It might just need 1 or 2 sentences out of that document. So by chunking it, you can ensure that only relevant information is getting passed to the prompt. The third step is to take each of these chunks and translate them into the text embeddings we saw on the previous slide. So what this does is it'll take a chunk of text and translate it into a vector or a set of numbers that represents the meaning of that text. Finally, we'll take all of these numbers, all these vectors, and load them into a vector database over which we can do the text embedding based search we saw on the previous slide. So now that we have a basic understanding of RAG and some key concepts surrounding it, let's see what this looks like in code. Here we're going to improve the YouTube comment responder from the previous video with RAG. We're going to provide the fine-tuned model from the previous video, articles from my Medium blog, so that it can better respond to technical data science questions. And so this example is available on Google Colab as well as in the GitHub repository. The articles that we use for the RAG system are also available on the GitHub, and the fine-tuned model is available on the Hugging Face Hub. So we start by importing all the proper libraries. This is code imported from the Google Colab, so there are a few libraries that are not standard, including Llama Index, the PEFT library, which is the parameter efficient fine-tuning library from Hugging Face. There's Auto GPTQ, which we need to import the fine-tuned model, as well as Optimum and Bits and Bytes. And if you're not running on Colab, also make sure that you install the Transformers library from Hugging Face. With all the libraries installed, we can just import a bunch of things from Llama Index. Next, we're going to set up the knowledge base. There are a few settings we need to configure in order to do this. First of which is the embedding model. The default embedding model on Llama Index is actually OpenAI's, but for this example, I wanted to keep everything within the Hugging Face ecosystem. So I used this Hugging Face embedding object, which allows us to use any embedding model available on the Hugging Face Hub. So I went with this one from BAAI. It's called BGE small en version 1.5, but there are hundreds, if not thousands, of embedding models available on the Hugging Face Hub. The next thing I do is set this LLM setting to none. And the reason I do this is that it gives me a bit more flexibility in configuring the prompt that I pass into the fine-tuned model. And then two things I set here are the chunk size, which I go with 256 characters, and the chunk overlap. This wasn't something I talked about, but we can also have some overlap in between the chunks, and this just helps avoid abruptly chopping a chunk in the middle of a key idea or piece of information that you want to pass into the model. With all these settings configured, we can create this list of documents using this simple directory reader object and the load dataset method. Here I have a folder called articles, which contains 3 articles in a PDF format from my Medium blog. And what happens is this line of code will just automatically go through, read the PDFs, chunk it, and store them in this list called documents. So there's actually a lot of magic happening under the hood here. The next thing I do is just a little bit of ad hoc pre-processing of the text. There are chunks that don't include any relevant information to the meat of the article itself. And the reason is these PDFs were printed directly from the Medium website. So there's a lot of text that is before and after the article itself that's not really relevant to the use case here. So here are just 3 ad hoc rules I created for filtering chunks. The first thing I remove is any chunk that includes the text member only story. The reason is this will typically be the text before the article, and it'll look something like this. It'll say member only story, then it'll have the title of the article, and then it'll have my name, the author's name, and then it'll say like where it was published. It was 11-minute read, when it was published, and it'll have the image caption and some just irrelevant text to the article itself. Another rule I use here is that I remove any chunk that includes the data entrepreneurs. This is text I include in the footer of each of my articles, which links the reader to the data entrepreneurs community. So you can see what that might look like is this is the last sentence of the article Although each approach has its limitations, they provide practitioners with quantitative ways of comparing the fat-tailedness of empirical data. Probably not helpful to any questions that you're going to ask about this article, and most of it is just text from the footer of the article. And then finally, I remove any chunk that has min read, which typically comes up in the recommendations after the article. So we can kind of see that in this chunk of text here. And of course, this isn't a super robust way of filtering the chunks, but a lot of times your pre-processing doesn't have to be perfect. It just really has to be good enough for the particular use case. And then finally, we can store the remaining chunks, these remaining 61 chunks, into a vector data store using this line of code. So now we have our knowledge base set up. So index is our vector database that we're going to be using for retrieval. With a knowledge base set up, the next thing we're going to set up is the retriever. First, we're going to define the number of docs to retrieve from the knowledge base, and then we're going to pass that into this vector index retriever object. The two things we need to pass here are the index, or the vector database, and the number of chunks to return from the search. Next, we assemble the query engine. So the query engine brings everything together. It takes in the user query and spits out the relevant context. And so we can use the query engine in the following way. So let's say the query is, what is fat-tailedness, which is the same technical question we passed to the fine-tuned model in the previous video of this series. And the query engine spits out this response object, which includes the top 3 most relevant chunks, but it also includes a lot of other information, such as the file name that the chunk was retrieved from, the page number, the date accessed, and some other metadata. So in order to take this response and turn it into something we can actually pass to a large language model, we'll need to do a little reformatting, which I do in this chunk of code here, and then we can print what that looks like. And so this text is probably small on your screen, but you can see that there are 3 chunks of text, and this is ready to go and be passed into a prompt and subsequently fed into a large language model. So at this point, we now have all the ingredients of our RAG module. We have our knowledge base, which was created using 3 PDFs, and then we set up the retrieval step, which takes in a user query and returns the relevant context from the knowledge base. So the next thing we need to do is to import the fine-tuned model so that we can generate a response to the user query. And so here we're importing a few things from the PEFT and transformers library. This is the base model that we fine-tuned in the previous video. And then here we transform the base model into the fine-tuned model based on the config file available on the Hugging Face Hub. And then we load the tokenizer. This is all stuff I reviewed in the previous video of this series, so I would check that out if you're curious to learn more. So now that we have the fine-tuned model imported, let's use it to respond to a technical question without using the RAG system. So the way that'll look is we'll create a prompt. This is the same prompt from the previous video, and I'm creating a prompt template using a lambda function, which will dynamically take the instruction string here and the user comment, which I define here, to create the prompt. So when we print it, it looks something like this, where we have the instruction start and end special tokens here. We have the instruction string here, and this goes on for a long time. And then here we have the comment. So with that prompt defined, we can pass the prompt into our tokenizer to translate it from words into tokens. We can then pass those tokens into our model to generate a response, and then we can print the output. This is what the model says without any context from the RAG system. Great question. Fat-tailedness is a statistical property of a distribution. In simple terms, it refers to the presence of extreme outliers or heavy tails in the distribution. For instance, consider the distribution of heights in a population. A normal distribution would have most people clustered around an average height, with a few people deviating slightly slightly from the mean. However, in a fat-tailed distribution, you would observe a larger number of people being significantly taller or shorter than the average. In finance, fat-tailedness is often used to describe the presence of extreme market moves or outliers in financial returns. It's an important concept in risk management and financial modeling. I hope this helps. Let me know if you have any questions. ShawGPT. Overall, the tone and the format is really good here. It explains things in simple terms. However, the description here doesn't really match the description in my video on fat-tailedness or the article on fat-tailedness. So let's see what happens when we inject the proper context into the prompt using the RAG system created earlier. We'll again create a lambda function. So here we're not just passing in the comments, but we're also going to pass in the context of the comment. And so this is something we'll get from our RAG system. But given that we have both, we'll have the same instruction string as before, but now we're going to inject the context into the prompt, and then we'll put the comment in the same place as it was before. So with this new prompt template, we can pass in the context and comment to get a new prompt. We'll pass in the prompt to the tokenizer in exactly the same way as before to generate tokens. Then we'll pass those tokens into the model to generate an output, and then we'll print the results. Here's the model's response when we include context using RAG. Great question. Fat-tailedness is a property of a distribution that describes how much the presence of extreme values, rare events, affects the overall statistics of the distribution. In the context of the video, the author discusses how mediocristan and extremistan distributions differ in terms of fat-tailedness. Mediocristan distributions have a relatively small impact from extreme values, while extremistan distributions are heavily influenced by extreme values. The author also mentions that fat-tailedness is a more general concept than specific distributions like Pareto or power laws. Instead, it lives on a spectrum ranging from thin-tailed Gaussian to very fat-tailed Pareto 80-20. I hope that clarifies things a bit. Let me know if you have any questions, ChatGPT. So this does a much better job at capturing the way I described fat-tailedness in my video. It defines fat-tailedness as how much rare events drive the overall statistics of a distribution, and it even talks about mediocristan and extremistan, which is something I talked about in the video to frame the difference between thin-tailed and fat-tailed distributions. I also like that it mentioned that fat-tailedness is not like a binary thing, which is something I talked about in the video, but rather it lives on a spectrum from not fat-tailed to very fat-tailed. Looking ahead to the next video of the series, I'm going to dive more deeply into text embeddings, which was an essential part of the RAG system. So I'll talk in greater detail about text embeddings and discuss two major use cases, namely semantic search and text classification. If you enjoyed this video and you want to learn more, check out the blog in Towards Data Science. And even though this is a member-only story, you can access it completely for free using the friend link in the description below. And as always, thank you so much for your time, and thanks for watching.